screen with you. So first of all, good morning. And we are start the second lecture about the variability of the ocean. And just want to recall what, oh, first of all, can you hear me?
Yes.
Okay, very good. Sometimes it's so embarrassing to speak in front of a screen and not knowing if there's anybody on the other side. So great to have someone that replay to me. Okay, yeah. So let's go back to the one of the last slides that we comment yesterday, and we started with the analysis of the scale variability of the ocean, and we start to discuss the seasonal cycle in the tropics. I just want to comment again some points of this slide. Essentially, the important issue for us is that at the equator, the annular signal is due to wind. Obviously, sun is always burning in this belt, and so the wind is the modulator of the annular signal. And however, SST is also important, as we saw in its interaction with the winds, exchanging heat from or receiving heat from evaporation and in this sense, the very issue is the coupling between atmosphere and ocean gives way to the seasonal signal. Now we abandon the warmer and pleasant water of the tropics and move to the mid-latitude seasonal cycle. And here the things behave slightly different. Let's go to give more detail on what is the most evident, most characteristic feature of mid-latitude upper ocean, which is the seasonal cycle of the ocean mixed layer. Ocean mixed layer is also present as tropics, but its variability is not governed by the same process as in the mid-latitude. And ocean mixed layer is, by definition, is the ocean region adjacent to air-sea interface. His striking characteristics is the fact that it's very well mixed, and the temperature and salinity and also density are uniform. You can see here in this schematics that temperature, salinity, and therefore the density are more or less constant in a upper layer. And as you see, the shape of temperature and salinity in general has this kind of structure and behavior. Why? Because density should be lighter at surface and denser in depth in order to guarantee the static stability of the water column. And if you don't have, if this steady stability is not respected, have the collapse of the water column, have convection. So the denser water falls down and is replaced by lighter water from below. But this is another issue. Maybe we can touch it marginally in the course of this lecture, but at the moment, what we have to retain is the fact that we have a specific boundary layer at the upper part of the ocean that is well mixed. And this is, well, an approximation, obviously, well, because there are forcing that continuously acts on this slab, on this layer. And essentially, you have on the top, you have air-sea interaction, wave motion, wave breaking, and so on. So exchanges of energy, momentum, turbulent energy with the atmosphere. And on the bottom, you have the ocean interiors, which have different characteristics. As you can see here, temperature is generally much lower, salinity tends to be higher, and also density is higher. And in a quiescent ocean, on the long run, the homogenization of the upper part will be complete unless forcing field can restructure, recreate this mixing. To go a bit more in detail, we can identify 4 different regions in this apparently purely homogeneous layer. This is homogeneous in terms of properties, but there are significant departure in terms of chemical properties and also in terms of velocity and turbulence. We have a very thin molecular sublayer. This sort of very shallow film, a few millimeters thick, that acts as an interface between atmosphere and the ocean interior. It's very important because every exchange of gases and also the interface with the atmosphere goes through this interface. And even more important from a practical point of view, the temperature of this skin layer, as it is called frequently, is the temperature that is detected by satellites. Satellites can detect the skin layer temperature, not the bulk temperature of the ocean, neither the temperature of the mixed layer. And this is particularly critical during the day where very strong temperature gradient takes place in a very upper layer of the ocean when the ocean is calm and the wave steering is reduced. The second sublayer is a couple of meters thick, is the layer that is directly influenced by wave motion. You may remember that wave doesn't move the water mass, but the water parcel under wave motion just move around its equilibrium position in a circular or subcircular wave. And this obviously doesn't change that much the properties, but surely change the velocity. Then we have the bulk of the ocean mixer layer, which depends on the condition. It could be minimum 10 to 100, even more in other in winter condition in some places. And at the bottom, this the bulk of the ocean mixer layer, we have the entrainment sublayer. Entrainment as a terminology that is quite used, frequently used in turbulence, that identify the process that transport properties from one quiescent layer into a turbulent one by turbulent processes. We'll go back to this point in the far. Just a matter of terminology. Most probably you have already went across them during this course. Thermocline, halocline, pycnocline identify the rapid transition zone, which is 10 meter or more thick, that you can find here at the base of the ocean mixer layer. This is more or less definition, but as I told you, we are in a layer that geostrophy, for example, is not fully respected, because we have forcing fields that significantly depart the water dynamics from purely geostrophic equilibrium or balance. And also we have a structure that is dynamically adjust between the forcing fields and dissipation processes. Let's give a look at this slide on your right side. This is temperature. Temperature is very often considered as one good proxy of the structure of the ocean mixer layer. And for example, you can easily detect that there is a homogeneous part that goes, in this case, up to 100 meters. This is a even more common depth that can be found in open ocean. This is a very famous weather station set in open ocean called Papa. And but you see that this mixer layer in December very deep. On the contrary, is much shallower and has less well mixed part in the surface. We can go from 20 meters to even more in April, which the maximum deepening is reached. And so this is clearly a seasonal cycle. It's quite evident. You can go from very shallow to very deep and vice versa. And this is quite a common and recurrent feature all over the mid-latitude belt, say. This is what we see or we can observe. But on the other side, we have to give some dynamic explanation for that. Why we have this strong variability. And the answer is summarized in this cartoon, not very well nice in some from a graphical point of view, but very informative in my opinion. So ocean mixer layer is an interface as put between the ocean interior and atmosphere, and is subjected to the wind stress that imparts momentum and turbulence input by the shear, but also wind gives way to evaporation. You know, evaporation means that you cool water, so the temperature at the surface of the mixer layer changes because of evaporation. On the other hand, in atmosphere, you have clouds that can create rain or precipitation, can freshen the surface water, making it lighter and making or creating sort of a buoyancy input here. And clouds has also an important role in modulating the solar radiation, which again as a source of the shortwave radiation that has the major role in transporting the energy, the thermal energy, into the upper part of the water column. You may remember that large parts of the visible and infrared band of the electromagnetic waves coming from the sun are absorbed in the very few meters. Only some lengths, wavelength can penetrate, but the large part are absorbed in the surface. So we have at the upper part a number of processes that tend to densify evaporation or making lighter the upper part of the water column because of changes in the density due to temperature and precipitation. We have, as I told you, as important input of turbulence due to the shear created by the wind stress at the surface. And also, you see here the waves, also the wave can contribute to that. At the bottom, we have a modulation of the interface, so the picnocline can move because there are internal waves, there are waves that behave in the same way as the upper part of the ocean. So the fast gravity waves that we can find in the upper part of the ocean. But here, the return force that govern the internal waves is the reduced gravity. So they move much slower because the gravity is a gravity that takes into account that there are two mass, one lighter above and another one denser, but the density gradient is small, and so the frequency of the internal waves is lower. Nevertheless, internal waves can modulate the mixer layer. We didn't mention here one of the most most famous and well-studied boundary layer property, which is the Ekman layer that you may have already heard during this course. Ekman layer is the effect of the propagation of the wind stress along the water column under the Coriolis force effect. And why this is not taken into account? Because in practice, in the ocean mixed layer, there is a part that somehow responds as the Ekman theory predicts, but it takes place in a very limited part of the year, because the conditions should be very, very calm, and wind should blow constantly in the same direction. You shouldn't have too much turbulence, or the turbulence should be constant, and so on. So the ideal condition and the ideal solution, which is a steady state solution, that is obtained by Ekman theory, cannot be applied. And even the Ekman transport that is guaranteed or estimated as a 90 degree on your right in the Boreal hemisphere is never found in reality. You can have an Ekman transport, but generally the angle is much lower, just because the departure from the theoretical condition are substantial. Nevertheless, you can have or may find also Ekman transport here, and also Ekman transport and Ekman layer can additionally modify the surface current in a very near to the surface. I forgot to mention that when you look at the scale of the Ekman propagation, it's order of maximum 10 meters, while the mixed layer is can be much deeper. Okay. I have to mention one thing here. We saw that the annual cycle of the mixed layer is quite effective, quite well described by temperature, and we saw that there are many processes that interact with that, and they have this annual variability. So solar radiation changes at mid-latitude significantly during the year. The wind regime do the same. All storms and perturbation are again seasonally dependent. But that's good. But the very characteristic is the fact that the ocean mixed layer is very well mixed, and why all these forces produce this mixing. Steering is obtained by the shear due to the wind stress exerted at the surface. Wave and wave breaking also contribute to the steering, and also the buoyancy fluxes. If you have during night cooling, the denser water in the surface goes down because they are light, denser than the surrounding water, and this creates also an additional steering. This happens at the surface. At the bottom is the things are more or less similar. Different processes act at the bottom, but create the same effect. So the entrainment, as I told you, given by a large turbulent head in the OML, mix the denser fluid from below into OML. So from upper part, upper layer to the lower layer, turbulence is the dominant process that tend to homogenize properties, momentum, and also biochemical parameters within this layer. Probably it's worth to discuss a bit more about the two different or dominant processes that mixes this layer. And Brenner and Greg also pointed out that you could use even two different definition. One is the mixed layer, which is they call the zone of a relatively homogeneous water determined by the history of mixing. And while mixing or turbulent layer is the zone in which mixing is currently active. So here you have the well, look at this the plate on your left, and you can have this area, which represents, you see here, the mixed layer. The mixed layer is limited by, for example, a thermocline or picocline, but this means that in the past, some process acted here in order to guarantee the homogenization of the variables. In practice, the mixing layer is the area which is actively mixed in this moment. For example, the wind stress is here working in order to homogenize the upper parts, even if this is the heat fluxes are heating this area. So if you have a net input of solar energy or thermal energy, stratification should take place. However, the wind-driven mixing tend to homogenize the effect in the upper part. The lower part is not affected because the radiation cannot reach the deeper part. Differently, the matter is different when you have a negative heat loss. In this case, the surface water gets denser and falls down, and obviously for continuity, some water parcel or water flask goes up in order to maintain the mass balance, and this creates a mixed layer. So I partially agree with that, is more a definition, but what is important is to keep in mind that we can have an active mixing layer and a mixed layer which is originated by, for example, convection. But what we learned from that, we learned that we can have two different kind of forcing. One is the shear-driven mixing, which is mechanical energy, essentially. The other one is convection-driven, so thermal energy. So one part is related to the mechanics. The other one is to changes in density. We forgot here the surface wave breaking that also contributes to turbulent kinetic energy. And plus other, for example, precipitation, for example, internal wave breaking. So there are other processes, but let's keep the the, explanation as simple as possible, because even if this layer is so shallow compared to the average depth of the ocean, and it's important to reduce, well, or to identify the dominant processes, and this shallow area is so important for the exchanges of energy, momentum, gases, and other other properties of the ocean. That's is important to understand perfectly. Ocean interior has not direct connection with atmosphere. Only through the ocean mixer layer this happens. So the dynamics of the mixer layer, in a way or the other, on the long run, is also connected to what will happen in the ocean interior. We spoke about processes. We look at the cartoons. We look at theoretical or well, more generic discussion of what are the forcing fields. But what are data? Let's give a look at this plot. We have the temperature, 15 months here, and depth. In black, you have the mixed layer depth calculated in terms of temperature, and in color, you have the temperature profile, the reddish, the warmer, the bluish, the colder. You can see you have the base at about below 100 meters, that the temperature is constantly about 5 degrees. But what happens surface is quite more dynamic. Let's start and looking at winter, January, February, March in oceanography. And we can see that practically the whole water column up to this interface below 100 meters is occupied by a cold, deep water. The deep water has the same properties as those we can find at the surface. It is due to the fact that during winter, the heat fluxes are negative, so the shortwave radiation is less than latent and the other sensible and long wave radiation that go outside. So the heat balance is negative and the surface water gets cooler. This results in a deep ocean mixer layer. What happens when the wind stress reduce and the solar radiation gets stronger? Progressively, the surface layer gets warmer and warmer and affects also the deeper part. So the combination of increased solar radiation, net heat fluxes, and reduction of the wind stress, so the turbulent energy, turbulent mixing is also reduced, gives way a very nice or very well structured thermocline. So we can even detect a thermocline that is not more than 20 meters in August, September. This homogeneous warm water creates at its base a density barrier at the base of the thermocline. What does it mean? It doesn't mean that if you want to mix by turbulence the large scale eddies that encompass the whole mixed layer. This should do more work to entrain water on the bottom layer. And so the fluxes, the turbulent fluxes at the base of the bottom layer are reduced. So the two elements contribute to self-sustain or self-intensify the upper layer. You have a shallower upper layer, which are very well isolated with the bottom, or and with strong strong positive heat fluxes. The heat fluxes makes warmer the upper part, but this increase the temperature gradient, and also the density gradient is increased, and so the turbulence flux due to entrainment at the base of the ocean mixer layer is also reduced. So you have the very nice summer picture that you can find here is this red spot. In autumn, this condition are progressively gets less effective. So the solar radiation is less positive, so the heat flux is decreased, and the wind are more intense, so the wind steering and the associated wave steering is increased, and progressively the deepening of the mixer layer is stronger. You can also see that the thermal energy is constantly reduced. This means that the temperature gradient at the base of the mixer layer is also reduced, and entrainment can be more effective. And this progressively, we are going back to the initial condition we found in January, so in the previous month, in previous winter. And this is more or less what we find and in open ocean at sea. This has been detected in the northwest Pacific, but more or less, obviously the values can different if you get what you observe the cycle in Mediterranean or in Atlantic. The number are different, but the shape is quite similar. You can have some shift in the maximum of the temperature. Conceptually, but the mechanism is the same. The forcing factor are the same. The intensity or the relative intensity could be different, but the conceptual model is absolutely similar. And this can give us the opportunity to make some consideration on that. Generally, in oceanography, deals with the lateral movement. The currents are essentially understood as a 2D current, and even the momentum equation, you may remember, are split in two parts. One is the horizontal one, so the horizontal current is governed by the momentum equation, and you can simplify the vertical momentum equation by hydrostatic approximation. So the vertical velocity, which is much smaller in intensity compared to the horizontal one is neglected as prognostic variables just calculated through the continuity equation. This is a technical issue. I want to mention, but I forget. Let's for the moment forget it. But what is the message? The message is, even in the formulation of the governing equation for the ocean equation, the horizontal part is assumed as more relevant. Instead, ocean mixed layer are 2D, but it's not horizontal. The direction or the dimension that we consider here is the vertical one. And this means that we have to change a bit our understanding and our approach. Vertical processes are important, are dominant here. And which are the dominant processes here? The diffusion, turbulent diffusion of energy from upper part and lower part, possibly also advection, but diffusion or turbulent diffusion are the crucial one. And since the overall layer or the upper layer is homogenized, we can even think about the possibility to integrate all the layer in a, let's say, single slab. And this can give us the two major approaches that are used for modeling ocean mixed layer. We don't want to go into detail of the technicalities of the model, but this helps us understand what are the dominant processes and which are the possible response to this kind of approach. Bulk model are the simplest one, has been proposed many years ago. I think the first of bulk models are more than 60-year-old. And basically, the assumption is that the momentum heat balance of the entire mixed layer are homogeneous and respond immediately as of the in the sense that there are no delay in the propagation of the signal along the water column, and all the action of the momentum, buoyancy, flux at the ocean surface at the base of the mixed layer are immediately transferred to the bulk of the ocean middle layer. That it makes this formulation is simple because you can reduce the dimension of the problem. However, and you can express or may express, as we saw in the next slide, this dynamics in terms of temperature and depth of the mixed layer. So we want to know which is the thermal energy and which is the potential energy associated to the deepening or shielding of the mixed layer. These are the two elementary two characteristics we want to describe in order to mimic the behavior of a mixed layer. Which are the problem for that? We have to parameterize it. We cannot describe directly through the equation, but we just parameterize the advance and retreat of ML under the action of surface momentum and buoyancy flexes. And this means that we have to take into account that the penetration turbulence generated by surface under the adverse action of stabilizing buoyancy fluxes the surface should be taken into account. So we cannot forget that if you have the heating of the upper layer, this is a barrier that prevents the penetration of turbulence stress from surface below. And again, the same problem at the bottom. These are physical processes that cannot be represented, but they should be taken into account with the judicious definition to some specific constant of fluxes. And I want to discuss with you this one of the most famous bulk model for the mixed layer. This is called Krauss-Turner bulk model that's from the author and that we originally proposed in a paper, a seminal paper of 1967. They made a lot of assumptions. First, the ocean is horizontally homogeneous. So we can forget lateral advection, we can forget lateral diffusion, we can forget all the anomalies in temperature or salinity that can be present laterally. And we assume, which is quite sensible assumption, that exists a vertically homogeneous or uniform layer in terms of properties and also shear. So turbulence is stationary. And also we can write a vertically integrated budget and for scalar momentum. So everything is collapsed in one slab. But we can allow a variability of this slab layer, slab depth, and also the temperature associated to the slab can change according to the exchange with atmosphere in terms of heat fluxes and also in terms of entrainment of thermal properties of the entrained water at the bottom of the. We assume that there are gradient discontinuous at the mixed layer bottom, which is quite fair assumption. And also we have dissipative processes inside the mixed layer, but this dissipation is known that end up in a changing of temperature because all the mechanical energy at the end of the process is transforming in thermal energy. But we just disregard this effect. These are basic assumptions, which are, well, a bit critical, but not that far from what we have seen in reality. So now we have the more mathematical part. My intention is just to discuss the two equations that govern this slab model, not looking at the solution, but looking at the composition of the terms that describe the dynamics, the ocean mixed layer model. And it can give us some hint to understand a bit more in detail which are the driving mechanism that change the temperature and depth. And we have two equations, one for the thermal energy, and the other one is the mechanical energy. We saw before the shear driven changes and buoyancy driven changes. The thermal energy, essentially, the change in thermal energy is obtained or is written in the first term on the left-hand side of the the first equation. You can have the thermal capacity multiplied by the density, which means the mass per unit volume, multiplied by H. This means it is integrated all over the water column, and this is the time rate of change of the temperature of mixed layer. If you look at the rho CVT is the heat content. So this means how the heat content integrated all over the water column, homogeneous. So it's depending on H changes. How this term change, how the heat content in the water column, in the mixed layer change with time. It depends on the RC net heat fluxes. If the heat fluxes can increase, also the temperature increase. If the RC net fluxes goes negative, or the tendency of the temperature will be negative. So we have a cooling. But this is not the only process. This is a process at the surface, or we have another process here, which is connected to the bottom turbulent flux, is the entrainment. We have again the term depending of density and specific heat here, and this is multiplied by del T. Del T is the temperature jump between mixed layer and the temperature of the ocean interior. And we have another term, which is a lambda, which is a Heaviside function. It is positive, is one when the mixed layer goes down and zero otherwise. So what does it mean? If you have a lowering of mixed layer because of mechanical entrainment, mechanical mixing due to the entrainment on new water from below, well, this term is has to be considered, and lambda is 1. Conversely, if you have a reduction of the mixed layer depth, so H goes lower, you have a so-called detrainment phase. So the part of the mixed layer is no longer mixed and gets instead included outside the mixing area. And so no bottom turbulent flux is active anymore. And so this term is not calculated, and lambda is 0. So this term is active when the mixed layer goes down. So essentially in autumn and in winter. In summer, this term is less effective. So we have two component, one due to atmosphere, the other one is to the turbulent input from the bottom. These two terms changes the temperature. A bit more complicated term equation we have for the mechanical energy. We express everything in terms of the changes in potential energy due to the temperature. This is the first step. This is integrated again along the water column, and this is changes due to temperature. The potential energy due to temperature is changes also because we have a potential energy change due to the bottom turbulent flux. We can detect again the same kind of bottom turbulent flux as we parameterize it on the in the thermal energy equation, but this is integrating all over the water column and is again depending on the entrainment factor. Again, this will be positive if we have this potential energy input due to the bottom turbulent flux. In case the entrainment factor will be 0, again, this this term will be neglected. Which are the change of potential energy is subjected to two forcing. One is the dissipation due to shear turbulent fluxes. And again, we have the two terms that we know exactly, the density and specific heat, but we have another term which is new, and this is depends on M, which is the measure of the efficiency of the mixing, which depends in turn by the efficiency of the wind mixing and the density of the water, the density of the air. This is the relations that is being applied in order to calculate this efficiency of the mixing. And U third is the so-called the friction velocity. Friction velocity is assumed to be the velocity that can be obtained by dividing the wind stress by rho and taking his square root. And it's essentially or you may interpret it as the velocity that is at the interface that imparts the turbulent component at the ocean interior. It is known by the theory that the square of friction velocity is proportional to dissipation. So we have a sort of coefficient that modulate the dissipation, and the friction velocity term that define the amount of dynamical amount of turbulence that is dissipated with that. We have also a term connected to a gravitational term and thermal expansion that also, if positive, will reduce this effect. If negative or less than 1, this increase further the efficiency of the mix. And then we have a final final term that depends of the total heat content and the fluxes, obviously, and this take into account the work against the thermostratification that should be done. So we don't want to go too much into detail, but essentially we have 4 terms for mechanical energy. One is the potential energy due to the stratification temperature. The other one is the potential energy changes due to the bottom turbulent fluxes that contribute to these changes. and the two are balanced by dissipation by shear turbulent flux that reduce obviously the potential energy and the work against to the stratification. With these two equations in two unknown, which is the temperature Tm, the temperature of the mixer layer, and H, which is the mixer layer depth, can find or can find a solution. It's not my intention to go into detail how to solve it, but it's important to set the equation this way. So we can use this simplified approach to find two simple solution that can help understand the two limits, two extreme situation that can be helpful to gain a deeper insight in the dynamics of the ocean mixer layer. We assume that we don't have any turbulent entrainment, and we have no changes, for example, in the heat in the depth of the mixer layer, and we can simplify the above equation for the diabatic case, where the changes of the total heat content, as you see here, well, before we can simplify the thermal energy equation in this way. We don't have any entrainment, and we can rearrange the equation this way. These two are assumed to be at the moment constant, and we can just rewrite this way. So the changes in the thermal energy, it depends essentially by the heat flux divided by H, and this is quite simple equation that explain and or help understand the effect of the thermal energy over the ocean mixer layer. And in the other case, we can have another simplified equation where only entrainment takes place. Again, we see that the changes in the temperature all over the mixer layer is due to the changes in depth due, multiplied by the temperature jump at the base of the mixer layer. These are only two simplification of the above equation under idealized condition. In one case, depends on heat flux, and the other one, how different is the temperature at the sea bottom. Okay, let's go back to the seasonal cycle and how the water column behave all over 1 year. And I mentioned the importance of the ocean mixer layer for as an interface between atmosphere and ocean interior, but we see that there have also important impact on the biology, on the biogeochemistry of the ocean, and also on the carbon cycle, so on the climate on the long run. There are also other important contributions. One of them is the fact that we are, or there are some expectation to make long-term prediction, looking at the memory that the mixed layer can give or can retain into the ocean immediately below the summer mixed layer. What I would try to explain you that the facts that you have a specific condition during winter in terms of temperature and salinity. This condition can be used to make better long-term atmospheric prediction on seasonal scale. We have to remember that the weather prediction are good at a lower, let's say, deterministic scale of 10, 15 days, and in which the ocean play well, a minor role. Whenever you go longer, the ocean atmosphere system cannot be disentangled, and the active role of the ocean should be taken into account. And I'll go to explain you one interesting case for that. And this is connected to the reemergence mechanism. It's called reemergence mechanism. Let's give a look at the at the winter, at the seasonal cycle of the mixed layer. And let's give a look at this winter here. We saw before that during winter, the water column is homogenized or is cooled or almost homogenized up to 100, even more meters. We can have two conditions. One in which you have a strong surface anomaly compared to the standard one that mix up the water column up to, in this case, let's say more than 100 meters. And assuming that the regular seasonal cycle has started with a mixing in this region of less of 50. When you have the regular seasonal cycle up to 50 meters, then you have the heating during summer, and then this water is mixed up due to the heat fluxes, and the memory of the initial condition are somehow, in some sense, smeared out by the summer season. When you have the winter, the autumn condition, you have start here again, the negative, again, negative fluxes again. This H larger than 0 is connected to this arrow. So summer you have a heating, a stratification. In this period, the heating are again negative, and the deepening of mixed layer involved through entertainment the conditions that are found here. And this condition somehow reflects the dense water, or the cool water formed during the, winter. And these are are mixed here, and this effect is probably less, has a limited effect on the condition of the surface water in autumn. But let's make an example in which the dense water formed or the mixed layer is much deeper during winter. And the surface flux anomalies creates a SST anomaly that spread all over the water column as in one. So the major difference is here is in the quantity and the quality. The water are more are cooler, and the mixed layer depth is deeper. The heat fluxes in winter and create again also ocean mixed layer surface that progressively reinforce during summer, and the this SST anomaly are the previous SST anomalies found in ocean now are found in ocean interior are detached by surface. So the ocean mixed layer act as a barrier between the condition of the ocean interior that are below the seasonal shoaling of the mixed layer. And this well-formed mixed layer prevent the exchanges of heat with the rest of the surface layer. And this anomaly in depth persists here in this area. What happened in autumn or late autumn? These anomalies are preserved by the seasonal ocean mixed layer. When the stratification collapses and the mixed layer deepens, the entrainment of this anomalous low temperature provokes a decrease of the temperature in the anomalous decrease of the ocean mixed layer. So this reemergence of the condition of January is guaranteed by the fact that during summer you have the decoupling of the upper layer to the lower layer, where the memory of the condition of winter are retained and are this condition reemerge during the fall-winter mixing. What does it mean? Is that this means that if you have a good understanding of what happened in winter, and if the winter is particularly severe, we can have some chance by exploiting this mechanism to make some prediction at seasonal scale of what happened after the summer autumn collapse of the mixed layer, because the condition, the temperature and the depth of the ocean mixed layer will depend not only to the forcing, but also, and first and foremost in this case, by the emergence of the preserved condition of the ocean deep ocean mixed layer characteristics all over the summer period in depth. And this process is known to be crucial when seasonal prediction of the weather are done, and most attention in research is paid also exactly in this field to make seasonal prediction more reliable. Okay, let's go a bit more let's go to look at more in detail some uh, uh, fields of the mixed layer dynamic depth as obtained by data. So we have discussed a bit theory, a bit model. Then let's give a look at what happened in reality. What you see here is the map of the world, and you see there are two different scales, unfortunately. Let's give a look at the Boreal Winter, and you see that mixed layer can reach very deep value in northeastern North Atlantic, and also as can be relatively deep also in some part of the mid-latitude in the North Pacific and North Atlantic. These areas are so deep because there are areas, especially here and here, are area where this is Labrador Sea, Immigrant Basin, and where a dense water formation is made. So you may have heard about this process from Miro. So you have convection that reach very deep layer, and this is also reflected on that. But also at mid-latitude, the value are considerably high, up to 150 meter and so on. While in the tropics, the value are less. Looking at this part, then the scale in September are different. The interest is connected to the equatorial phase or the tropical phase more than the polar one. And you see that there are quite a significant variability in tropical, subtropical, Pacific Ocean and also Atlantic Ocean, while the northern part of the Atlantic is very shallow. So we have exactly the reversal of what happened in winter, but the intensity is quite different. So the mixed layer depth is much deeper during winter, and then the eventual deepening in September in tropical area in Pacific and in Atlantic. But this is quite obvious because the changes, as we saw, of the ocean mixed layer or the seasonal cycle in the tropics reflects a different kind of processes, and also are more shallow and affect in a different way the upper layer compared to what happened in the mid latitude. And we saw that we have a interesting, well-shaped gradient between the coastal off equator water here, while in the equator you have a slightly constant value both in Atlantic and in in the Pacific area. And I just want to close with a small part of the basic topic of the course of these lectures, giving well, some hints on what happened in from biogeochemistry when you have such a variable mixed layer. I just want to introduce a couple of comments or concepts that could be useful. You see that light, as I told you, tend to diminish in depth. So the highest light is available at surface, and then exponentially decrease, going down to almost zero after 100 meters. Instead, nutrients have the opposite shape. There are few of them in upper layer and higher in the deeper layer, because I can anticipate the plankton, the algae uptake a nutrient for their growth. So when you have algae, nutrient are generally low, and where the algae are not, because the light is no longer present, the nutrients are high. These are the typical stratified ocean that we can let's say face during stratification period. The growth or the algae can produce more, can growth. Can growth because the growth rate is stimulated by the availability of carbon, nutrient, and light in the upper part, but surely cannot grow without light. So we have a sort of photosynthetic gain or growth rate that goes as the red light. And this is instead a sort of constant respiration, which is the loss, or integrate all the losses that the phytoplankton dynamics. You can have a growth due to the photosynthetic activity and some losses that are connected to the basic functioning of the cells. What happened? How the dynamic of phytoplankton is affected by the mixed layer dynamics. Better to introduce a concept which is the critical depth. The critical depth is the depth which the vertical integral of phytoplankton growth equals the vertical integral of losses of biomass. So in the critical depth, guarantee that on average, the two components, the growth and the loss, are balanced. So if you integrate the phytoplankton all over this depth, from surface to critical depth, the tendency is null. So no changes due to natural variability. In winter, you have the mixed layer, which is generally deeper to the critical depth. That means that the properties in the mixed layer are known to be mixed, but the small algae are also distributed uniformly in the water column. So they are also brought outside their comfort zone, say, no light, so they cannot produce. And this has effects the capability to growth, while the respiration is more or less constant. So the fact is to reduce the concentration, the phytoplankton growth, and make this negative. During winter, respiration, so the losses exceed the growth, and the total amount of the phytoplankton during the deep mixed layer is low. In summer, instead, you have that the having, assuming as constant the losses, assuming as constant the growth, the mixed layer is lower, so the cells are confined in the upper part, and in this case, the critical depth is quite far, it's not reached by the mixing. The cell lives in a, well, better for them conditions, more light and warmer. So also temperature has an accelerating effect on the dynamic of the phytoplankton growth, and the photosynthesis exceed respiration. So this is a very crude and very basic explanation why in summer you can have more phytoplankton in the upper layer than in winter, and this is called the Sverge paradigm, which is crude in the description, but interesting because it highlights the relationship between the depth and the critical depth and the growth and the losses of the small algae, which play a so important role as a basis of the whole food chain and also as a carbon sink. I think my time is over, and I would close my discussion today here. And if you have any question, please do now. Otherwise, you have my email, or you can send me some email for clarification, and I'll give you tomorrow the first two slides, two sets of slides reviewed, and in couple in 1 week or so, I'll give you also some notes. They're not all the arguments are already included in the notes, so please take your notes, take the note yourself, and but you can also use the slides as a guideline for your study and so on. But in 1 week, I'll give you also some more detailed notes, not only the slides. Okay, I'll give you, probably I use Slack for sharing the material. Okay, thank you for your attention, and see you on Monday, right?
Okay, thank
Bye-bye.
you. Thank you.
Ciao, ciao.
Bye.
Thank you. Bye.
Thank you.